macroscopic, so that's like, gases are so small. That's like the great big overall view of them. The macroscopic properties of a gas, pressure, temperature, are explained in terms of microscopic components, such as, and what are these microscopic components? How about we just say extremely small size or small particles? So like we look at the small particles and we say, okay, the effect on each small particle is very small, but if you add it all up, it's like a huge effect overall on the whole system. So this thing is called the kinetic molecular theory of gases, and this helps us describe ideal gases. More on ideal gases coming up, but in order to apply the kinetic model of gases, we have these assumptions, and that's what we were just talking about. Okay, so one is that individual gas volume is negligible. This means if you are in a stadium and the stadium like is sealed, like it's a covered sealed stadium, and you have a little tiny fly in the stadium, compared to the size of the stadium, the fly's volume is negligible. Or imagine even smaller, like a little teeny tiny piece of sand. That's what this means, that the each individual gas volume is negligible compared to the size of the container that it's in. We also assume they undergo no intermolecular attractions or repulsions. That kind of means that when those gas molecules hit each other, it's not like they are temporarily attracted to each other and want to hang out next to each other for a few seconds before then bounding on their way. All the gases that you saw in that simulation would bounce into someone else, and then they would immediately bounce away. They didn't like kind of stick around for a little bit. That's what those attractions would do. And repulsions would keep them from even bouncing. They'd get close, and then they'd immediately go away from each other. So we don't have that. Then for an ideal gas. And then particles are in continuous forward motion, if you want to call that forward motion. They're in continuous, constant, straight motion. Collisions between gas particles are completely elastic. Again, that just means that we don't lose a little bit of energy to, the gases scuffing along the side of the container or something like that. And then here's the biggie. The average kinetic energy is the same for all gases at a given temperature, regardless of the identity. This might be surprising, but like you saw, the kinetic energy of a sample increases with temperature. So at any certain temperature, again, the average kinetic energy that they're bouncing off of each other with, it does stay the same for all of them at a given temperature. So at increased temperature, they will have higher average kinetic energy. And again, average because they're going to be slowing when they hit each other little and speeding up when they hit each other little. So we mentioned ideal gases. What are ideal gases? Well, ideal gases, they are negligible compared to this container size. We already talked about that. So they're teeny tiny compared to how big the container that they're in is. They do have average kinetic energy, and that is proportional to the temperature in Kelvin, and the collisions are elastic. Again, you don't lose energy. Those are ideal gases. And in reality, there's only like one or two ideal gases. So if there's only a few, why do calculations and why overly focus on this idea of an ideal gas? Well, it's because the math is easy. Well, easier. And it's because when we're talking about like it's not an exact fit, it's just in the little teeny details, like in some of the decimal places, they aren't the same. So the math is easier for those ideal gases. And also, like it's really good to teach with because you can see general trends with the regular gas equation. Let me just show you why you would prefer to use a smaller equation. And this is what you get when you're dealing with not ideal gases. See all those little variables in there? This is what you get when you're dealing with ideal gases. See the difference? The A actually is standing for attractive forces, and the B is actually representing size. So it's for most atoms, you can't really completely say that their size is negligible, but we can approximate it that way. and we can get a lot of information about the gas and be very, very close on our numbers.